Okay, so now we are going to be talking about moving to non-continuum behavior. So, non-continuum behavior says that for particles that are smaller than a particular size, and for small particles of the order of less than half a micron in diameter, and when we are talking in general about particles, typically we are using rho p is equal to 1 gram per centimeter cubed, and this is why it is called unit density, right. Unit density just means 1, but it is in gram per centimeter cubed, it is not in so it is something to just keep in mind, right. So, it is same as the density of water, right. So, for small particles of this kind of unit density, half a micron or smaller, they start experiencing slip. So, they experience slip, and therefore, the no slip boundary condition no longer holds, right. So, then how do we account for this slip is all the whole story about non-continuum effects. Okay. So, in order to account for slip, and therefore its effect on drag, we have to understand a characteristic length of the suspending medium. In this case, the suspending medium is the gas, right. We will call it gas suspending medium, and so I guess we can just maybe finish the whole continuum this thing by saying that we had put up the idea of Newton's general law, which is really acting on very, very inertial particles, and then the idea that when you come down to Stokes, and the fact that a friction coefficient is then 3 pi mu dp is the friction coefficient when you multiply it by the relative velocity between the fluid and the particle, which is V infinity in this case, then you get the drag force. So, this coefficient is called the friction coefficient, right. So, then we want to understand the characteristic length of the suspending medium, and any guesses what it is? Yes, okay. So, the characteristic length of the suspending medium is the mean free path. So, let us take a look at the idea that gas molecules at a particular temperature and pressure then have a certain thermal velocity that is associated with them. This is the fraction of molecules with velocities in a differential velocity range dc is given by the 4 pi c squared. Then you have the moment you start seeing this m by kt, where m is a molecular mass, k is a Boltzmann constant, and T is your absolute temperature. So, m is molecular mass, and of course, you can equivalently be using molar mass and universal gas constant. This is Boltzmann constant. So, Boltzmann constant is nothing but R by N, which is 1.38 into 10 to the minus 23 joule per Kelvin, right. So, once you start seeing things that are looking like this, you know that somehow kinetic theory is coming into play. So, then what we have is we go ahead and calculate a mean velocity of the gas molecules, which is 8 RT by pi m or 8 kBT by pi molecular mass to the half, and we note that this bears a relationship to the thermal velocity, which is induced by the temperature itself, and rough orders of magnitude for these of the order of maybe 300 and of the order of maybe 400, 450 is what we have. So, you are really thinking of gas molecules as zipping around, I mean really bullet speeds, right. So, this is what gas molecules are doing. Then what is this concept of mean free path between collisions is that we designate mean free path by lambda, and mean free path is nothing but this average speed of travel by a certain collision rate, right. So, you really have a meter per second, right, and a certain collision frequency or a collision rate, which is number of collisions. Whenever you have a number, it is dimensionless, so per second, and this is what we have as the mean free path. And we want then to understand what is a collision rate. So, this collision rate can be derived once again from kinetic theory, and it is shown to be root 2 pi. I do not know whether to write sigma square because we have been using sigma for standard deviation, but I will explain what this sigma is. So, this is nothing but what is called collision diameter, right. So, collision diameter, then for molecules, we understand that you have gas molecules that are colliding with each other and so on and so forth. Even though there is this so called hard sphere sort of feeling, we all really know that there is all these electronic shells and so on and so forth. So, it is sort of like the if we were to think of it as two different molecules here, it is the distance of approach, right. So, based on whatever the potentials are, how close they come before they start then repulsing and going away. So, this distance between centers, minimum distance centers at the point of approach, the closest point of approach, that is what is called as a collision diameter. And this collision diameter for air at STP is of the order of 37 nanometers. Okay. So, now that we have of the order of 37 nanometers, we can then go ahead and we know that this molecular number concentration is nothing but a P by kBT, right, which is P then is whatever your pressure. If it is standard atmosphere, it is I'll just write everything down. So, this can be 1.013 into 10 to the minus 5 Newton per meter square. Kb we already wrote, T is a 298 Kelvin, right, and we said that this is then of the order of 460 or so meter per second, right. So, with these values, we can go ahead and calculate for ourselves a value of mean free path of gas molecules air, for example, by taking the mean molecular weight of air as 29. Yes. 1.0 10 to the 5. Correct, correct. So, then we go ahead and find a value for lambda by putting all these values in there, and what we end up with is 0.065 micron or 65 nanometer. Is again air at STP, the mean molecular weight of air is 29 if you are looking at the 80% nitrogen, 20% oxygen roughly as your molecular weight average, right? So you then understand that the suspending gas has a characteristic length which is tiny by any macroscopic kind of understanding, 65 nanometer, right? And so then we are talking about being able to find out particle diameters as vis-a-vis this length. And so here we go. And so we can basically say that we want to now define a parameter which is called Knudsen number, Knudsen, Knudsen number, which is defined in terms of 2 lambda by dp. So lambda is the mean free path as we just wrote, and dp is the particle diameter. And you can see that Knudsen number is inversely proportional to particle diameter, okay? It's something for which you have to kind of start getting a feel for it, for the fact that it is inversely proportional and not directly proportional. So the larger the particle is, the smaller the Knudsen number. The smaller the particle is, the larger the Knudsen number. And so we were trying to give you an explanation of this idea of free molecular regime and continuum regime last time. This is just saying the same things that we had on the board, which is telling you that the mean free path then is of the order of 65 nanometers, and the Knudsen number is what we are going to use to define regimes of particle behavior, right? And what are these regimes? Then these regimes are continuum, particle sizes get much larger than the mean free path, and therefore Knudsen number is tending to 0. Free molecular, the particle is starting sort of to behave, we won't say like a molecule because it is so much more massive than a molecule, but it's starting to get to that kind of behavior, and this is where you have Knudsen number tending to infinity is the way that it's written, right? But you have particle sizes much smaller than this 65 nanometer, right? So you're really starting to talk about particles maybe 10 nanometer or 20 nanometer and much smaller before you start looking at them as having free molecular behavior. But you can see now that there's going to be a large number of particles with size ranges that doesn't strictly fit into continuum and doesn't strictly fit into free molecular, right? So this is the thing, and to give you an explanation, what is shown there as A, what really is the particle seeing? The particle is seeing a lot of molecules that are impinging on its surface. The molecules that are leaving the particle are encountering other molecules very frequently, right? And that's what really gives you the sort of continuum behavior with a lot of sort of collisions and a lot of drag on the particle. By the time you get into free molecular regime, there's many molecules that are kind of missing, hitting the particle. Some of them encounter the particle, and when a molecule reflects off the surface or bounces off the surface, collides and goes away, then it may or may not encounter another molecule very quickly, right? So that is sort of what the particle is seeing a lot of empty space, if you will, right? Because it happens to be so small itself. If the particle were looking out into the gas, it's seeing a lot of space. Every now and then a molecule zips by, every now and then a molecule actually collides with it, right? While here in continuum, the particle is seeing molecules all around it all the time and is getting a very high frequency of collision. And then of course we have this transition regime, and many particles then fall in this kind of size range vis-a-vis the mean free path of air, and we have to describe their behavior as well, right? So this is what we have, and so now we will write for each one of these what is a drag coefficient, right? So we said for continuum regime, we already had this idea that the drag coefficient is going to be 3 pi mu dp from Stokes' law, and notice it has a dependence, direct dependence on dp, right? So we can say Fc has a direct dependence on dp, right? What is called free molecular regime. In free molecular regime, we have this form of a drag coefficient, 2/3 dp square rho. You start seeing kinetic theory type of sort of term over here. This is what is called the Epstein formula, and we may, if somebody is interested, post a derivation of this for you. We won't go into it in the middle of the class time. This is purely theoretical, but we have this idea of accommodation, which is every collision does not, transfer, relate to an exchange in momentum between the molecule and the particle. And so we have an experimentally determined what's called accommodation coefficient, and there is a particular term where this alpha is an accommodation coefficient, and this has to be measured experimentally. So the accommodation coefficient is measured experimentally, and it is of the order of 0.9, right? But you can also assume it as 1 for practical purposes as well. Now what do we do with this transition regime? So if we want a way to discuss all the regimes and be able to treat it, what we do is we take the continuum regime version and we correct it by a term, and this term is what is called the Cunningham slip factor. And again, the slip factor comes from a fit to experimental data, whether we're talking about, the kind of Millikan oil drop experiment type of things where we're really trying to balance forces on a particle. You would have a particle in a flow field and have some charges on it and have a certain electrical field to balance the forces. So you are leading to an electrodynamic levitation of the particle, and then being able to do this over a set of relative velocities, a set of particle sizes, a set of particle characteristics, then we end up with an expression for Cc, and this Cunningham slip factor, what is it, 2 lambda by dp? Yes, you have a Knudsen number here, and then you start having some empirical coefficients here into both the continuum regime and the free molecular regime over a period of time. So, over a period of particle sizes. So, in fact, because of that, very often people use the transition regime expression for calculating without really getting into, oh, am I really in free molecular regime, am I really in continuum regime, and I can go with the transition regime formula, right. So, what is the magnitude of this correction factor and how much is it going to change the drag on the particle? So, here let us take a look at this. So, you start seeing that this is again air at STP. When we start putting the values of particle size into the slip factor, by the time you are at a 0.1 micron particle, your drag has gone down by almost a factor of 3. By the time 0.01, another order of magnitude, so 22, and then 200, more than 200 by the time you are in a 1 nanometer particle size, right. So, what is really happening is that, remember, the slip factor is in the denominator of the drag coefficient. So, the larger the value of the slip factor, the smaller is the value of the friction coefficient, and therefore, the entire drag force is becoming smaller and smaller. So, the particle is slipping in a sense that you do not have this idea of so many molecules close to the particle surface that are really able to hold the particle, and you then see that your it is very important, and there is a very linear dependence, if you would, with a very significant large values. By the time you reach 1 micron, if you are not using a slip correction, you are off from Stokes' law by 16%, and then by the time you are going to larger particle sizes, you are pretty much Stokesian. Your Cunningham slip factor is tending to 1, right. So, large particle sizes, Cunningham slip factor tending to 1, you are going back and recovering the continuum form of the drag coefficient, right. So, this is the story of non-continuum behavior, which typically we do not encounter in many other physical systems other than aerosols, right. So, this is something which is sort of very special to aerosol science, if you will, and we teach it, we understand, and what does this do to drag on a particle. So, let us take a look at a few more things. Here you have got a feeling for the fact that the drag became so much less, the drag kind of tended to Stokesian drag after larger than 1 micron and so on. So, this is now telling you a few things, which is how does mean free path vary with altitude for people who work in the atmosphere, right. So, you have both a temperature dependence and a pressure dependence, okay. So, you have a temperature dependence and a pressure dependence over there. What do you think is changing more rapidly with altitude in the atmosphere? Is it the temperature or is it the pressure? Yeah? Oh, okay. So, I think the atmospheric people would really kind of have an answer to this, that pressure really changes by many orders of magnitude as you go from the surface to 12 kilometer, etc., right? So you're really going from 1000 millibar to 50 or 20 or 5 or something, right? So you really have many orders of magnitude change in the pressure, which then what will that do? That is going to increase your mean free path, right? So you have this increase in mean free path, which is fairly steep increase, right? And we're not just talking, so these are all small particles, even though this is micron, so they are getting to be still somewhat larger. So what is this telling you? This is telling you that even larger particles can begin to slip when we're under low pressures, right? So this is a particle characteristics that is used in designing what are called low pressure impactors. So low pressure impactors to be able to fractionate particles and atmospheric pressure, and we told you there are impactors, you have different size ranges of particles being collected on different stages, and you can just about separate up till about a half a micron in diameter. But to be able to separate smaller particles into different size ranges, you have to have either low pressures or some other mechanisms to do that, right? So that is one thing, and the other thing that is showing over here, that's being shown over here, is dP variability. Over here we're looking at 10 micron, 1 micron green, 0.1 micron orange, etc. In the atmosphere, and here this is a figure from Hind's book, which is showing you the slip correction factor, that is change with dP, and because you're looking at many differences in particle sizes, it's being shown as 3 different lines for 3 different ranges, which you can read off the bottom, right? So slip correction is very important for small particles at STP. It becomes important even for larger particles when you go to much smaller pressures, right? Which means that those particles then also start not experiencing so much drag, right? Any questions on this? Okay, then here are some questions, and let's go around the room, see who wants to. I mean, much of this is repeating what we've just said, but it's a quick recap. So we'll start from this end. Anybody want to answer any questions? Darshil always looks down very shyly, but you can answer some questions. Yeah. Yeah, increasing altitude, decreasing pressure, therefore we have an increase in the mean free path of gas molecules. Correct. And because we have that increase in mean free path, we're really going to have a reduced drag or a reduced friction coefficient for the particle. Okay, anybody else? Anything, Azam? Okay. Correct. Correct. So we had this mean free path has a direct dependence on temperature. If you were holding pressure constant, then increasing temperature without changing pressure is going to reduce the mean free path. High pressures, that, basically you're saying that if I have very, very high pressure environments, even the smallest of particles will start exhibiting continuum type of behavior. Yeah.
But so at constant volume it will not change.
Oh, at constant volume, I didn't say constant pressure. Okay, all right. Huh?
It doesn't change.
Yeah, at constant volume it doesn't change. At constant pressure, it will increase. Correct, correct. Anyone else want to speak up with something? So, here the, fourth question is sort of ill-posed in a sense because your particle sizes are changing as well. That is why one of them happens to be continuum, the other one happens to be free molecular. But you're basically saying that for a fixed given relative velocity, it's going to depend on whether or not the magnitude of the friction coefficient itself, and the friction coefficient is going to be much smaller in free molecular than it's going to be in continuum, right? So, that's sort of so this is the other thing, which is that you're used to thinking about particles in terms of settling velocities and so on and so forth, right? And this is a standard thing that we've all been doing for a long time in our training. So, what is a reduced drag coefficient going to do to the velocity? It will increase the velocity, right? So, let us just go ahead and take that up, and this is something that is going to be boring and a repeat for most of you, which is settling of a sphere in a stationary fluid. The only thing that's different this time is that we're also going to include the slip factor, right? So, that's the only difference. So, we have a stationary fluid over here. You have the usual, mg in this direction. You have your drag force in the opposite direction, and your fluid velocity is equal to 0 because it is stationary fluid. This is something you've seen so often that most of you are probably falling asleep right now. The only change over here is that your drag force is now going to be corrected by a Cunningham slip factor. Next topic, when we talk about inertial deposition, we'll talk about the fact that the du by dt also starts affecting it, and then you have the history term also, and we will give you the answer to that question as soon as we start talking about the next topic. And I don't want to be a spoiler and give you the answer right away. So, indeed, when you're talking about fast velocities of projection, you're going to have the inviscid fluid sort of pushing back on the particles. So, the du by dt term also will affect drag, and then the history term will also affect. Yeah, we can check that. I mean, that's sort of standard in the textbooks. Yeah. Yeah. So, okay, everybody, here's interesting homework for you. Go back and check whether the collision diameter, what is the correct order of collision diameter at STP, and yeah. Yeah, no, I mean, these are all interesting. I mean, we're used to kind of approaching it in a particular way and taking certain things for granted from textbooks, but it's also a good idea to go back and look at them, right? Okay, so yeah, and I think some more over here really just talking about the fact that you have these, it varies as a function of particle diameter, but will also vary as a function of pressure because of the pressure influence on the mean free path. And so this just gives you the order of variation, and you can see, of course, that the particle diameter based change is of course a lot more dramatic than any other change on drag, right? And therefore, this is basically telling you terminal settling velocity at these different temperatures and pressures, right? Okay, so now I think we have enough time to move to a very interesting topic, which is related to equivalent diameters, right. So, we said that more or less in many cases we do have a certain measurement method, and therefore an equivalent diameter based on the measurement method, and therefore, you know, we have the idea of optical equivalent diameters, which are, you know, sort of more difficult to sort of deconvolute in terms of how is the optical diameter then related to the physical diameter, because you also end up having a refractive index effect on the whole thing. But per se, we have this idea of being able to define equivalent diameters for a variety of things. And so, one of them of course is non-sphericity. And how does non-sphericity affect drag? And so, we have one thing related to non-sphericity, and the other one which says over there aerodynamic diameter. So, volume equivalent diameter is when you have a non-spherical particle, you essentially take the volume and come up with an equivalent diameter. The Stokes diameter is diameter of the spherical particle having the same density through. Filtration is also based on the same, but with impaction you could get sizes. But to get numbers, there's also another instrument that combines electrical along with impaction called an electrical low pressure impactor. And so, one needed to go to mobility, being able to somehow bring charges into the measurement method to be able to start counting particles and making measurements of particles that were much smaller. And then of course, highly irregular particles are an entirely different situation. And so, let's basically, you know, put maybe the kind of expressions that we would encounter over here. There is, in terms of shape, we have this concept of a dynamic shape factor chi, and why do we use, you know, the word dynamic? The moment you start having non-sphericity, and we can just, you know, use a cylinder as the simplest sort of example over here, then you can have the cylinder in many different orientations in terms of its settling, right? And so, you could have different orientations over here. And so, this is called dynamic shape factor because it has to be averaged over all the orientations, right, when you have a non-spherical in this case we will say particle, right. So, then here the way that we do it is that we said we are going to equate the terminal settling velocity of each one of them. So, we go ahead and we say that, you know, we had this. So, this is our usual
then it will settle into that orientation also, regardless of how you start.
You're saying that it will accommodate into an orientation of the least drag in case of. And also the fact that we are correcting with a slip factor, right? So we're saying that we may not always be in a Stokes regime. The moment you're moving away, and then we'll talk next after we finish inertial impaction on particle diffusivity. So you're really going to not just have a particle tumbling, but you're going to have a particle that's moving around on its own and tumbling, right? And so indeed it's somewhat different from a macroscopic kind of idea of what happens to particles. But yeah, you have this idea then that you have orientation averaging, which becomes important. I think just some more of similar stuff over here, which is giving you an idea of the magnitude of change, which is if you're going from 4,000 to 1,000 kg per meter cube, which is one unit density is the last one. You're talking about a very significant change in diameter over here. And each of them has the same equivalent settling velocity is what is being shown. And this is sort of a more complicated thing, which I'm just going to kind of describe for you the physics of it without going into a step-by-step derivation. Fractals are very important and very interesting, both in the fact that their optical properties as well as their physical properties are very strongly influenced by the fact that they have this very interesting shape. So typically a fractal is described in terms of its two things. One thing which is related to what is called the monomer size over here, and the other is related to the radius of gyration. So how lacy different fractal structures by assuming different physics of orientation. So there were thousands of papers that were published in diffusion limited diffusion limited aggregation and so on and so forth. When do you get particles that were more fluffy, less fluffy, and so on? Yeah.
So practically, how do we measure a fractal? I mean, mathematically we know we have the shape, so we can find out a fractal dimension. But for a material, let us say, how would we measure the fractal dimension?
How would we measure the fractal dimension itself? Or I mean, the imaging is the one way to measure both monomer size as well as physical extent, if you would. And there also you're getting a 2D image of a 3D structure. And so the one way in which these things are looked at is through mobility, right? So mobility, like we talked about, the moment you have a spherical particle and you have a fractal particle, the fractal particle is going to experience a lot more drag, right? And so the mobility then can be used to diagnose something related to the 3D structure of the particle. So in fact, Cl710 does, so he is at IIT Goa, an aerosol scientist. He does some of this kind of work where you're trying to use mobility measurements to then understand and recreate the entire fractal characteristics. Yeah. That certain types of what we call thermophoresis. thermophoretic methods of particle collection and deposition were used in order to not break up these kind of delicate fractal particles and be able to collect them without breakup compared to impaction, and then be able to visualize them better and so on and so forth. So, yeah, this is sort of I think where I wanted to get with equivalent diameters. We can put up something else for some discussion and then stop here today.
Particle doesn't go itself. The air let them go to that surface. If vehicle is running, it has air around it.
Right, but it will bring it close to some extent, and the last bit the particle has to do on its own. and so the last bit of travel the particle has to can't be helped by the gas anymore, and it has to decide in which way it's going to reach the surface and then how it's going to hold on to the surface. So yeah.
Near any surface, fluid doesn't penetrate.
Yeah.
Particles have to do
their own, they have to reach the surface somehow, and that is what we'll start.
And where you need all this.
And we'll start talking about the whole idea of inertial impaction, diffusive behavior and diffusive deposition, and what is called direct interception. And so these are the mechanisms of particle mechanics, and we'll finish. So I just had some things over here for, these are more sort of numerical types of small problems that you can. Tire wear. Yeah, no, I mean this is just that if you have tire wear particles that are emitted, then how long is it going to take to settle, and so on and so forth. So, I mean, I think one of the things you have to understand with many of these larger particles is that they do settle out of the atmosphere fairly close to sources, and it is really the much smaller particles that persist for longer periods of time in the atmosphere. So, unfortunately, there have been certain methods of that are being proposed to clean ambient air, which are not very effective, and that this kind of understanding is needs to be there, that it's not really some of the larger particles that we need to worry about. And if we are trying to do things like having either air blowers or even suction based sort of collection devices, you may be doing a lot more resuspension around the device than really cleaning particles out of the air, and so on and so forth. So, these have been some of the problems in teaching people about what really is a good air cleaning device or not.
One thing is, let the monsoon do its job.
Well, we can't, we do have clean air for the periods of rainfall, but I think the important thing which, as both in regulation and this thing, is the importance of emission control for clean air, because all societies that have had the history of going from polluted conditions to cleaner conditions have relied entirely on emission control in order to reach there. So, we have to take that seriously as a measure, an intervention measure, while we can have other measures for interim cases, like for example, the smog tower type of device, which can lead to air cleaning in certain realm around it, and so on and so forth.
And like in power plants,
Yes.
they use ESP.
Yes.
And they said we
we have designed specifically for this type of coal having this percentage of ash, but never looked at what is the chemical composition. And one of the problems were when they change a type of coal or use certain blends, efficiency of those devices drop from 99.9 to 99.95. But that slight change leads to increase the concentration from 100 micrometer per normal meter cube of air to triple of it.
Yeah, so really appreciate your bringing up gas cleaning in terms of thermal power. In India, we unfortunately have very high ash content coal, right? And so we're talking about mean ash content across all our coal fields and the coal utilization of the order of 40%. So 40% ash content in coal is very, very high. So at the end of it, from your coal combustor, you're going to have a massive both mass and number emission. So what is done is to have a set of multiple cyclones to remove the larger particles and then go to the electrostatic precipitators. As far as composition of the particles goes, with electrostatic precipitators, you really need to be able to charge the particles effectively to be able to then collect them. And as far as mineral particles, refractory particles go, they tend to have similar characteristics with respect to charging. I'm not very sure about the importance of chemical composition in particle charging and removal with electrostatic precipitation. Not sure it's going to have a very big role, but indeed changing the coal, changing the ash content, and the fact that if you have even the tiniest drop in efficiency of the device, you're going to have massive increases in the concentrations. All of those are indeed very true. Unfortunately, coal cleaning is very difficult to do and very expensive to do. So the other thing is to clean the ash from the coal before putting it into the power plants, but boilers, but we're not able to do that effectively. Okay, so yeah, we can stop here for today.